Hello everyone. Today I will show a video about the chaos and the Lyapunov exponent. And this presentation is including 4 parts. The first part is Lyapunov exponent. The second part is basic properties, and the third part is chaos checking. And the last part is about the significance about the Lyapunov exponent. Now welcome to the first part, where we will show you about the definition about the Lyapunov exponent. In mathematics, the Lyapunov exponent of a dynamical system is a quantity that characterizes the rate of separation of infinitesimally close trajectories. Quantitatively, two trajectories in phase space with initial separation vector diverge at a rate given by sigma zt equals to e the power of nanta t, the absolute value of sigma z 0, where nanta is the exponent. And the rate of separation can be different for different orientation of initial separation vector. Thus, there is a spectrum of Lyapunov exponents equal in number to the dimensionality of the phase space. It's common to refer the largest one as the maximum exponent, because it determines a notion of predictability of a dynamical system, which it can be called as chaotic. And the maximum Lyapunov exponent can be defined as follows: lambda equals to the limit of equals to 0, like this. And for discrete time systems, xn plus 1 equals to fxn for orbit starting with x0. This translates into this formula. In the second part, we will talk about the basic properties. If the system is conservative, for example, there is no dissipation, a volume element of the phase space will stay the same along a trajectory. Thus, the sum of all Lyapunov exponents must be 0 if the system is dissipative. So the sum of Lyapunov exponents is negative. And if the system is a flow and the trajectory does not converge to a single point, one exponent is always 0, then the Lyapunov exponent corresponding to the eigenvalue of L with an eigenvector in the direction of the flow. And the third part is about the chaos checking. Now we will show a suppose that f has a stable p cycle containing the point x0. Show that the Lyapunov exponent lambda equal less than 0. If the circle is super stable, show that lambda equals to minus infinity. As usual, we convert questions about p-cycle of f into questions about the fixed points of f the power p. Since x0 is an element of a p-cycle, x0 is a fixed point of f the power p. By assumption, the circle is stable. Hence, the multiplier fp x0, the absolute value, is less than 1. Therefore, a result that we'll use in a moment is like the line of f the power p x0 less than ln y equals to 0. Next, observe that for a p-cycle, we can know that lambda equals to this value, since the same p terms keeps appearing in the infinite sum. Finally, using the chain rule, we can get that this value is less than 0 as desired. If the circle is super stable, then this equals to 0 by the definition. And then the second example concerns the tangent map. Now we come to the fourth part about the significance. The Lyapunov spectrum can be used to give an estimate of the rate of entropy production of the fractal dimension and of the Hausdorff dimension of the considered dynamical system, in particular from the knowledge of the Lyapunov spectrum. It is possible to obtain the so-called Lyapunov dimension, which is defined as follows. Where k is the maximum integer such that the sum of the k largest exponents is still non-negative, dky represents an upper bound for the information dimension of the system. Moreover, the sum of all the positive Lyapunov exponents gives an estimate of this accordingly to Pence's theorem. Along with widely used numerical methods for estimating and computing the dimension, there is an effective analytic approach, which is based on the direct Lyapunov method with special functions. The Lyapunov exponents of bounded trajectory and the Lyapunov dimension of an attractor are invariant on the homomorphism of the phase space. And now today is about our presentation. Thank you, everyone.